Let's have a talk about acid-base indicators. We've used them before in grade 10 to determine whether a solution is acidic or basic. We've used them in grade 11 when we've done our titration lab, but we've never really discussed what they are. And what an acid-base indicator is a weak acid where its ionized and unionized forms have different colors. So for example, in this case, I have a weak acid that is red in color, but when it ionizes to form its anion, it's blue in color. And so if I place this in a different pH levels solutions, it will drive the equation one way or another and give me a solution that's red, blue, or some combination of the two. Okay? So the color, as we said, the color is determined by Le Chatelier's principle. If I increase my hydronium ion concentration, then my equation will shift to the left, and I will have mainly an ionized acid. If I decrease my hydronium ion concentration in a basic solution, or I add OH minus, then I'll shift my equation to the right, and I'll have my ionized form. Now the pHs that this occurs depends on my indicator, because they are different weak acids and weak bases. So here we have a list of a variety of different indicators and the ranges over which they can test the pH. So for example, if I take Congo red changes in a pH range of between 3 and 5. And so in a pH below 3, it is not ionized at all. It exists as its unionized form. So it'd be blue. In a pH above 5, it's going to be completely ionized, and so it will be red. But in between 3 and 5, I'm going to have some that's not ionized and some that is, and so it'll be a purple color. Okay. Similarly, last year we used phenolphthalein, and phenolphthalein we used as our indicator, and in a pH below 8.2, it's colorless, and it's not ionized at all. But in a pH above 10, it's completely ionized, and it's red. But in between 8.2 and 10, it's a little bit ionized, and that gave us our faint pink, so we knew when to stop our titration. Now we can use these indicators in a variety of different ways to achieve different goals. One of them is, if I had a solution whose pH I didn't know, rather than doing a titration, I could add a variety of indicators to it, and it would give me a pH range. So for example, I have a solution of unknown pH, and I've added 4 indicators to it to try and determine its pH. So if I look at my first one, chlorophenol red is yellow in a pH below 5.2, red in a pH above 6.8, but in between 5.2 and 6.8, some of it will be yellow, some of it will be red, so I'd expect it to be orange. In this case, it's a yellow color, which indicates that its pH of the solution that it was added to is less than 5.2. When we look at bromothymol blue, it's yellow in a pH below 6, blue in a pH above 7.6, but in between that range, it has a pH, or a color, of. So we can see from our yellow color with our bromothymol blue that it has a pH less than 6. If we look at our methyl red, it has an orange color, so that tells us that its pH is between 4.8 and 6.0, because below 4.8 it's red, and above 6.0 it's yellow. But in this pH range, some of the acid will not be ionized, and some won't. And so I'll have a combination of the two colors, which will give me orange. Okay. And finally, we have our methyl red, which is yellow, and so that tells us that our pH is above 4.4. So now we can take all of these results together, and we can write a general range for the pH of this solution. And so this one tells us that it's above 4.4. This tells us it's below 6. We can narrow the range to 4.8 to 6 with this one, and then we can narrow it further and say that my pH is somewhere between 4.8 and 5.2. Now, last year we used our acid-base indicators when we're titrating. And when we titrate, regardless of the combination that we do, it's important that we pick an appropriate indicator. We want to pick an indicator which changes color around our expected equivalency point. So, as we looked at in our titration curves, the pH at equivalency for a combination of a strong acid with a strong base is 7. So therefore, I want to pick an indicator who changes color around a pH of 7. And I can look at their pKa values. And so any one of these 3 indicators would be suitable. And we would see that my bromothymol blue would be green, because below 6 it's yellow, above 7.6 is blue, so a pH of 7 will be a combination of the two, it'll be green. Likewise, litmus will be purple, it'll be a combination of the two colors, and phenol red will be orange, because it also will be a combination of the two colors. Similarly, if we looked at the titration of a weak acid with a strong base, I know that my pH at my equivalency point is above 7. In this case, it's 8.2. So therefore, I would look for an indicator that changes color around 8.2. And we have our thymol blue, but more importantly, we have our phenolphthalein that we used last year, which below 8.2 is colorless, and as we get to 8.2, above 10, it's red, and in this range, it's going to be faint pink. And so this is why last year we used phenolphthalein as our indicator.